Computer hardware, module 2. So today we're going to look at the hard disk drive and RAM. Both things are used to store information in different ways though. So let's go over that. There we go. So the hard disk drive, or HDD for short, most people don't call it a hard disk drive. Most people just call it a hard drive. And that's fine, but the reason why we don't call it a hard drive, or we shouldn't call it a hard drive, is because most people are going to want to shorten the acronym down to HD, and HD has a million other applications, whether that's high definition or heavy duty or whatnot. Hard disk drive is the technical term for it, and it is shortened down to HDD. This is a form of storage. Storage means that it stores information long term. Now this is important to remember. We're going to go over this in a little bit of detail. So if we're thinking about our human body alias again, we're thinking long-term memory, memories that we keep forever. And we have access to them at will whenever we need to. Sometimes we have to think hard at it, but usually we can remember what it is. So a hard disk drive, or HDD, is often referred to as long-term memory. So what exactly does that mean? Well, a hard disk drive, stores permanent data for future use. Pause there for a second. Permanent data. That means that it doesn't go away unless we manually erase it. We have to put effort out to get rid of it. And it's for future use. What that means is that usually this is information or data that you're storing like installs, like you've installed Microsoft Word or you've installed a video game. What that means is you've basically copied all the files over from the internet or a disk, wherever you got them from, and stored it in a secure location on your computer. Whenever you want to run that program, that information is then copied from there, copied, not taken, copied from that storage, that permanent storage, and then stored in a different location for current use. We'll get into that in a minute. So stores permanent data for future use, like programs or save files. So when you have a Microsoft Word file, a .docx file, what is happening here is you're working in temporary data, but whenever you hit that save button or autosave kicks in, then that information is then stored permanently on your hard disk drive. So this storage is considered non-volatile. Now, a lot of students get confused by the word volatile and non-volatile. Think about how you would use it in a sentence. Ooh, this situation is pretty volatile. It means unstable, not safe. So if it's non-volatile, that means it is safe. And in the world of computers, what that really means is, what if the power goes out? So if you're playing on your computer and the power goes out, or the power goes out, any data that's stored on the hard disk drive is still there, doesn't go away. So losing power does not cause the loss of data. So this storage is what's called secondary storage. You may think, but that's where we store all the important stuff. Why isn't it primary storage? Well, it's secondary storage because your computer doesn't look there first. It looks for the data in faster locations, primary storage locations. So this is the secondary storage. So how does it actually work? Well, this is where things get really interesting. The way that data is stored on these hard disk drives is you see those silver platters there. They're not actually silver, but you see these platters here. And what happens is the data is basically stored on them in sections. So imagine you cut it up like a pizza, okay? And then you draw circles around it from the center out. So what you end up with is all these wedges with kind of arc-shaped pieces in the wedges. Now, all the information that you want to store gets stored in one of those locations. Now, it gets cut up quite finely. And that data that you're trying to store is stored there using magnets. Now, remember, computers don't understand a whole lot. We talked earlier, and the CPU uses what's called binary data and manipulates binary data. When we're talking about a hard disk drive, it's storing that binary data, and it does so with magnets. Well, what is binary data? Well, the most basic form, it's a 1 or a 0, or a true or a false, meaning the same thing. 1 is true, 0 is false. In magnets, it's positive or negative. positive is a 1, negative is a 0. So it reads all this information very quickly. Now there's another aspect to this. It stores the data sequentially. What that means is it stores it in order. There's not a piece of it in one corner of a wedge and then another piece of the information in another area and then another piece in another area. And the reason being is that it would actually take too much time and effort for us to actually retrieve that information that's scattered throughout. And the reason being is that the way that this works is you can see the silver armature here, and that thing moves in and out to the center, to the edge. So it can get anywhere on that line. The platter itself, the silver disc, it spins. So imagine the piece of data we're looking for is right over here, let's say right up here. What would happen is the disc would have to spin around, bringing that piece closer over here, and then the arm would have to move out to the outside. Now imagine the next piece of data is way over here. Well, the disc would have to keep spinning around until it lines up, and then the arm would move in towards that data. So every time that you have to find a new piece of data, there's physical moving parts that take time to get there. You have to look for it. That's why we store the data in sequence, in order. So that means that if you have a piece of data right here where I'm pointing, the next piece will be right beside it, and then right beside it, and then right beside it. So that means that we have to spin the drive, or spin the disk all the way over here, and then move the armature, and then it reads that binary data. Is it positive or negative? And then it just spins a little bit more, grabs the next one. Spins a little bit more, grabs the next one, and so on and so forth. So this idea of sequential data is super important. I like to kind of compare this way of finding data as seeking. And what that means is, imagine for a second you're trying to get to your favorite part in a movie. Now, and if you're watching that movie on YouTube or something like that, you can just kind of click on the slider bar and it'll just pop to wherever you want to go. But pretend for a second this is the 80s and you wanted to watch a movie and it's on tape. You got to get to your favorite part. There's no jumping around that tape. You have to hold in that fast forward button until you get to the point you want to get to. Well, that's very similar to this disk. If we're trying to get to data over here, I can't just pop over there magically. I have to wait for the disk to get all the way around. I'm fast forwarding it to the part that I need to get to. So that's what it's like. It's like fast forwarding a movie to get to your favorite part. So where is the hard drive stored? Well, the hard disk drive is stored internally, typically. You can get external ones, but typically it's internal, and it's connected to the motherboard using a cable. And the reason being is it's okay to not have it directly attached to the motherboard. You might be thinking, but I need it to be fast. Well, the limitations on a hard drive speed are not the cable and the distance to travel to the CPU. The limitations on the hard drive are how fast can we spin that disk? The faster we can go, the more data we can access more quickly. But that speed is still slower than the speed of the information passing along the cable. So it's okay to run our data through a cable in this case. Right? And then the device itself is typically mounted in the tower in some way, usually in the rack and screwed into the side. Okay, so that's one piece. Let's talk about a little tidbit of information that I like. Every once in a while, you're going to see me drop one of these kind of nice to know pieces of information that are interesting. And you may actually see these things on a test or a quiz or something like that. So you should be looking at that. Here's our first piece of information. In 1956, the cost of storage space was $10 million per gigabyte in 1956. Of course, computers back then were the size of entire rooms. Today, you can get data storage at a whopping price of 3 cents per gigabyte. So it went from 10 million per gigabyte to 3 cents. That's crazy. Now, that's not even accounting for inflation. 10 million in 1956 is a far bigger number than 10 million in modern time. So there's actually an even bigger difference when you think about it. Okay, moving on. So let's talk about a few extra details about storage. Now, we already mentioned that we store data in binary. And binary is really just a sequence of ones and zeros. 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1. And it's up to the computer to interpret that information. Remember, the CPU interprets and manipulates data. It interprets that information and does a different action. So for example, if I'm using Microsoft Word and I hit the W key, the CPU is going to get a sequence of ones and zeros that represent the W key. And if I'm using Microsoft Word at the time, it's going to put a W on the screen. However, imagine I hit that same W key while I'm playing Call of Duty or Destiny or something like that, some first-person shooter. It's not going to write a W on the screen anymore. It's going to cause me to move forward. I'm going to walk forward because that's what W does in those games. So depending on what is the current active program, those ones and zeros, even though they're the same ones and zeros from before, will get interpreted differently. And that's really important in the big scheme of things. So data is stored on a computer as ones and zeros, binary data. Now, a single 1 or a 0 is called a bit. That is the smallest form of memory that exists, of storage that exists, smallest form of data. Like any form of measurement, we need units. So when we're referring to computer data, we typically talk in terms of bytes. Now, the equivalent of this in like regular measurement might be something like a millimeter or even a centimeter, I guess, because a centimeter is made up of 10 millimeters, whereas a byte is made up of 8 bits. 8 bits to a byte. I know that sounds weird, but it's 8 bits to a byte. So this is just a collection. It might be, for example, it might be 00001111. So that is 4 zeros followed by 4 ones. And I know from my experience that that is really a value of 15. And we can interpret that in any way. 15 might represent, I don't know, the 15th character in the alphabet. It might represent something completely different. It depends on the program currently running. So when data is stored, it's stored as these sequences of ones and zeros. So down below here, I've created a chart of all the different units of measure we have when we're talking about data. So what we see here is a single 1 or 0. Our smallest form of measurement is a bit. And obviously there is no short form for that. A bit is a bit. And it is 1/8 of a whole byte. The byte is the standard unit that we're going to use. We typically don't use bits, we use bytes. So 8 bits together make up 1 byte. Great. A kilobyte. Kilo means 1,000. Kilobyte, right? Just like a kilogram is 1,000 grams. A kilometer is 1,000 meters. A kilobyte is 1,000 bytes, but not really. It's almost 1,000 bytes. It's approximately 1,000 bytes. So kilo means 1,000, but it is approximately 1,000 bytes. What it actually is 1,024. And you may think 1,024. That's a really odd number. We can go into more detail about this, but suffice it to say, binary is made up of 2 possible digits, 0 and 1. 1,024 is the equivalent of 2 to the power of 10, and that's where that 1,024 comes. So every measurement above this is always just a multiple of 1,024. If you remember a few slides ago when we were talking about hertz, every bigger unit was always a multiple of 1,000. So when you're talking about frequency, you're multiplying by 1,000. When you're talking about data, we're multiplying by 1,024 to get to the next step. Okay? So a mega means a million, so it's about 1 million bytes. Gigabyte is about 1 billion bytes. Terabyte is about 1 trillion bytes. A little bit more than that. So you notice we have kilobyte, megabyte, gigabyte, and terabyte. There are no short forms for bit and byte. So why does this matter? Well, sometimes you may need to kind of go back and forth between these data sets. You may need to go back and forth between bits and kilobytes or gigabytes and megabytes. Why? Well, it depends on what you're doing in that given situation. But if you're a programmer, you're probably going to encounter this more than the average person. So let's think about how we can convert between all the different measurements, the different units. Well, it works the exact same way as converting units in anything else. We're either multiplying or we're dividing. If we have a bigger unit of measure, say megabytes, and I want to know how many bytes are in my megabytes, then I'm going to be multiplying because I'm going to have more. There's going to be more bytes than there are megabytes. If I have megabytes and I want to know how many terabytes I have that represent those megabytes, then I'm going to be dividing because I'm going to have less terabytes than I have megabytes. So let's see some examples of this. So conversion between the units. Follow these 3 simple rules and you'll get it every time. Now look over here on the right. You see this chart? I want you to try and memorize this chart. Bits, bytes, kilobytes, megabytes, gigabytes, terabytes. Are there bigger units of measure? Most definitely. Petabytes, xenobytes, and all these other big ones. And then the yottabytes, a ton of them. Anyways, so what you're going to do is you're going to follow, to do any conversion anytime, you're going to follow these 3 simple rules. First, when moving down the grid, you need to divide by 1024 each step. So if I'm on megabytes and I want to go to gigabytes, I'm going to divide by 1024. If I'm on megabytes and I want to go to terabytes, I'm going to divide by 1024 to get to gigabytes, and then I'm going to do it again to get to terabytes. Notice it says divide by 1024 for each step. Okay? When moving up the grid, you need to multiply by 1024 each step. There's one trick to the whole thing though. When you're moving between bits and bytes, it's always by a factor of 8. So you're either multiplying or dividing by a factor of 8. Why? Because there's only 8 bits in a byte. That's it. There's only 8 bits in a byte. So whenever you're going from bytes to bits, you're going to multiply by 8. Whenever you're going from bits to bytes, you're going to divide by 8. That's it. So let's look at an example. How many bits are in a 2 gigabyte USB flash drive? Now, some of you say, well, I can do this all in one step. And you probably can. And that's great. But I don't want you to make a mistake. So it's better to actually go step by step. So if you're starting at bits way up at the top and you need to get to gigabytes, that means we're going down, so we should be dividing. Okay, so we're going to divide by what? So if we're going from bits to bytes, we're always dividing by 8 according to step 3. So if we have 2 gigabytes and I want to divide there, sorry, I apologize. We're going from gigabytes to bits. I got backtracked there. I apologize. We're going from gigabytes to bits. So back that up. We're going to be multiplying each step of the way. So we're going up the chain. So we're going to be multiplying. So how many megabytes are in 2 gigabytes? Well, I know from simple math that 1 gigabyte is 1024 megabytes. So 2 of that is going to be 2048. Let's look at that math though. So if I'm going from gigabytes to megabytes, it's just going to be simply 2 times, because I have 2 gigabytes, times 1024, which gives us 2048 megabytes. But now I need to go up to kilobytes, and I'm going to follow the exact same process. I'm going to multiply what I have by 1024. So now I have 2048 multiplied by 1024, which is giving me 2,097,152 kilobytes. Still not done. I got to go to bytes now. So again, I'm going to be multiplying by 1024. And now I'm at 2 billion, a little bit over 2 billion. One more step, we haven't gone to bits yet. So we're at bytes and we're going to bits. Step 3 says we're going to multiply by 8. So we should have roughly about 8 times this number, which we do, 17 billion bytes, a little bit more than 17 billion bytes. That's how many, or sorry, bits. 17 billion bits. That's how many ones and zeros are on that flash drive. 17 billion. That's a lot. Now, most of you probably have flash drives substantially larger than that. Maybe 8 gigs, 16 gigs. I just bought one so I can store my videos on. That's a terabyte. A terabyte, which is 1024 gigabytes. Substantially bigger than this guy here, right? 512 times bigger. So you'd have to multiply that thing by 512 to get how many bits I'm looking at. Okay, so that's how we convert. You'll notice it says university only up here. That's because the college level of the course doesn't need to do this conversion. It's not part of the curriculum. So let's talk about the secondary storages and compare them a little bit. So we're only going to do this very quickly. in terms of all the different forms of secondary storage. So these are all the places where data is stored on a permanent basis. So we have hard disk drive, USB drive, solid state drives, and optical disks like CDs, DVDs, that kind of stuff. And this chart basically goes through and just compares how big their capacities are, how they compare when it comes to speed, so accessing, so reading and writing the data. Portability, can you walk around with it or is it stuck inside your computer? Price, how much is it per gigabyte? That's usually the measurement that we use. You saw that in previous slide where I said it was $10 million per gigabyte and now it's only 3 cents per gigabyte. And then what is the best use for these kinds of things? All right, so a hard disk drive, it stores the most amount of data typically. It's medium speed, relatively speaking, to everything else. It's not usually portable, although you can get external ones. Price, it is ridiculously inexpensive, super duper cheap. We saw 3 cents per gigabyte. And then what are these things best used for? Best used for storing large files, so large and a lot of files, right? You're going to see these things inside of desktops, laptops, things like that. And believe it or not, old iPods, that's one of the things that made them super popular, is they came with a 5 gigabyte hard drive built in, a little mini hard drive built right in. So you could store a ton of songs, which what was a ton of songs back then. So then we get a USB drive, which most of us carry around on us all the time. And they range in size from tiny to massive. They're typically in the medium speed range, but some of them, like the USB 3.0 through 3.1 ones, are quite a bit faster. So they can actually be quick. Very portable, sometimes too portable. Can't tell you how many times my flash drive has went through the washing machine because I forgot to take it out of my pocket. These things are pretty expensive per gigabyte. They're not that cheap. The terabyte one I just bought cost me, I think, $170 for a flash drive. But you go to Walmart and buy the small ones for 2 gigabytes, or they're 2 gigabytes for like $5. It all depends on how much storage you're actually going to be using. You can carry these things around with you. It's good for backing up data, that kind of stuff. Solid state drive. A solid state drive is kind of like a combination between a USB drive and a hard drive. It takes the technology of a USB drive, the stuff inside, and what we're about to talk about next, and combines that with the idea of a hard drive, the permanent storage. All right. Now these ones are really expensive, so typically they range in cost between 250 gigabytes, range in size 250 gigabytes to about 2 terabytes. You don't really find them much bigger than that because they get really expensive really fast. But they are lightning quick in terms of accessing data. Again, these things are not typically portable. You usually plug them directly into your tower, but not always. Like I said, very expensive. Where would you use this? When you're installing frequently used programs. So I have a solid state drive in my computer I'm currently using, and I have a regular hard drive. So all my programs that I use a lot, I will typically put on my solid state drive. So Windows is obviously installed on my solid state drive, and so are a lot of my games that I play a lot of, right? So like Civilization 6 or whatever it is, right? And then everything else I store on the hard drive because it's a lot bigger and a lot cheaper, but it's slower. So finally, the last one we're going to look at is the optical disc. Those plastic pieces, or those little pieces of plastic that basically can store a fair amount of data from 4.7 gigabytes, which is a standard DVD, I believe, yes, all the way to 50 gigabytes, which is your Blu-ray discs, right? These are super slow. They kind of work similarly to a hard disk drive in terms of storing data. So they store it in sequential circles as it spins, and they access it in the same way. They spin the disk till it gets to the right spot. The difference here is they don't have an armature that reads the data. What they have is a laser. The laser basically shoots up directly at the disk, and if it doesn't bounce directly back in the required amount of time, then basically it knows whether it's a 1 or a 0. Is it a deep pit or a shallow pit, depending on where that laser bounces off of. So that's our secondary storage devices. Okay. Where are we here? We're getting there. We're almost done. Oops. So the next one is random access memory, or RAM. Now, I don't really like this term random access memory because there's not really anything random about it. In this case, random means something completely different. It actually means direct. So, in my opinion, it probably should be called direct access memory, but they like to use the term random. Maybe they don't want to call it their damn memory. I don't know. So what is the human body alias for your RAM? Well, if the hard disk drive is your long-term memory, RAM is your short-term memory. It's for stuff that you just started using. It's stuff that's in use at the moment. It's temporary data that's currently in use. So if you open up a saved file from your computer, like a saved Word file, it doesn't actually use that original data. It makes a copy of that data, and then it copies it into your RAM. And then your RAM uses it, manipulates it, and changes it. And when you're ready to save, it then takes the manipulated version and saves over top of the original one on the hard drive. So it stores temporary data in use at the moment. So things like your files and save files, that kind of stuff that you're currently accessing. The storage is considered volatile. It is unstable. It means if the power goes out, so does your data. It's gone forever. Forever. So you got to be careful about this. This is why programs have implemented things like autosaves. Word didn't always have an autosave feature. Now, by default, I believe it autosaves your file every 5 minutes or so. I think, and you can actually change this number, but 5 minutes seems pretty reasonable in a program like that. So this storage is called primary storage because this is one of the first places that your computer is going to look for data, a primary location. Why? Because it is ridiculously fast. And there's two main reasons that it's ridiculously fast. First of all, there are no moving parts. So you don't have to wait for a moving part to get to a location. All right? The second reason is that it stores data electronically. It doesn't store data magnetically, it stores it electronically. So remember, we're talking about binary again. Binary, 1, 0. True, false. Positive, negative. And another one that represents binary again, voltage. High voltage is a 1, low voltage is a 0. And that's how the data is stored in RAM. High voltages and low voltages. All right? So what happens is, your computer says, open this file at this memory address. Now, a hard disk drive would have to spin up and move the arm to get to that memory address. But RAM, it kind of has like a table of contents, a lookup table, and it just jumps directly to the endpoint. It doesn't have to scan through everything, just it's there. Now, remember the analogy I had for a hard disk drive was like trying to get to your favorite part of a movie by fast forwarding it. You have to scan through the entire movie till you get there. If we're talking about RAM, you want to get to your favorite part of your movie, it's more like using the scene selection tool on your DVDs or whatever. You hit the scene selection, you choose the scene, you're there. So it's like a table of contents. It just pops there automatically. It's super duper fast. So where is RAM located? Well, this thing is all reliant on speed. So anything that's reliant on speed needs to be connected directly to the motherboard. So that's where these chips go. Now, the modules. I showed you in the first page of the motherboard where they go. There are those horizontal areas that you plug things in at the very bottom. They're usually pretty long. So this is an internal chip connected directly to the motherboard. All right, another useless piece of information that's interesting. Now, the last one we talked about was in 1956. The cost of storage was $10 million per gigabyte, but today it's only 3 cents per gigabyte. Now let's talk about RAM. RAM's much more expensive than storage space. In 1957, 1 year after the other one, the cost of RAM was $411,000-ish per megabyte. Per megabyte. So if we're comparing apples and oranges here, or we're comparing apples and apples, that means that we need to put this in gigabyte format. Well, we just learned how to convert megabytes to gigabytes. We just do what? We divide by 1,024. So that's what your cost is going to be, right? So that's a cost per megabyte. Sorry, multiplied by 1,024. Yes, you're going to multiply by 1,024. What does that actually mean? Well, roughly 1,000. That means you're looking at $411 million for a gigabyte. Remember, storage space was 10 million. This is 411 million per gigabyte. Or we look at this again, and the number per megabyte or per gigabyte goes off the charts. It's tiny. That one right there is not even 1 cent for a megabyte. But multiply by 1,000 and things change a little bit, right? Okay, that's our piece of information for now. We're almost done here. How much primary storage do I need in my computer? So this is all about the software and the tools that you use in your computer. So when you're going to purchase a computer, you want to buy the right amount of RAM for your purposes. So if you use large complex software like database, things like that, you're probably going to need at least 6 gigabytes. If you're playing advanced games, you're probably going to need at least 6 gigabytes. If you're playing very simplistic games like Facebook games and things like that, you don't need a lot of RAM, so you can have far less. To run internet browsers, you don't need a lot, so you can have far less. Programming, typically speaking, when we're programming, we're dealing with raw data. So, and the way that the memory works with that data, as well as all the different resources, typically we're going to need more than 6 gigabytes, not per program, but between that and the operating system, everything like that, you're going to need at least 6 gigabytes. Most office work, I say most because there are some exceptions, you don't need a lot of RAM. Here's the exception. When you're doing complex mathematics, like working with large Excel files, you need a ton of RAM. The bigger that Excel file, the more RAM you need because it's currently inside of your computer, and it needs that space. Now, actually, we're gonna move on from there. I don't want to get sidetracked. Last but not least, how much primary storage does my computer need? So the last one was how much do I need based on the software I use. Now let's talk about your computer. Now every computer has base functionality. So what is the amount of RAM it requires to run its base functionality? So if we're talking your standard computer, Windows PC, MacBook, things like that, these computers do a lot of different things. So you're probably going to need more than 6 gigabytes because they're doing all these things simultaneously. Some other examples that you might recognize. Most dedicated game machines have quite a bit of memory. So the Xbox One has 8 gigabytes of memory, but only 5 gigabytes of it is usable by you as the user. The other 3 gigabytes are consumed by the actual operating system. PS4 is very similar. It has 8 gigabytes, but only 4.5 of those gigabytes are actually usable by the user. The Nintendo Switch only has 4 gigabytes. It doesn't really need any more because it doesn't push the graphics that the other ones do. Smartphones. Smartphones are kind of like general purpose calculators. They're actually computers in our pockets. And if you look at this, the amount of storage space on these things is crazy. The iPhone has just as much as the Nintendo Switch. The Google Pixel 4 has a little bit less than the Xbox One and the PS4. And the new Galaxy S20 has 12 gigabytes of RAM. That's an intense amount of RAM. Then we get into dumb phones. Dumb phones are phones that aren't smartphones. Things like your old brick phones that basically were indestructible, but all they could do was call and maybe a little bit of texting. A flashback to the old school days of Nintendo 64. If you've ever seen one of these things, they had right in the very front of it, there was actually a little compartment that you could take off and you could actually see the RAM cartridge right there. And it was a whopping 4 megabytes, not gigabytes, megabytes. Megabytes. That means it's 1,000 times. It's got 1,000 times less than the iPhone 11. 1,000 times less than the iPhone 11. Now, there was a couple games that came out that required more memory, so they offered an upgrade package, an upgradable package, that basically allowed you to pop out that old 4 megabyte one and put in an 8 megabyte one. And that actually made a huge difference at the time, because you're talking mid to late 90s for this, so the amount of RAM was pretty small on most devices. Okay. So that's the end of the presentation. We have one more module after this covering our graphics card and a few different things, hardware and software. Other than that, keep going.